Okay. All right. Hello, everyone. My name is Ed McDonald. As of the last happy hour, I was the newest employee at Solution Street. I don't know if that's true anymore. I've been here for about 5 months, joined right after COVID, so I have not met a lot of you face-to-face yet. I'm presenting today an introduction to Kubernetes. As I mentioned to some people before the meeting started, please interrupt me if you have questions. I don't mind. I think that actually works a little bit better. And I may tell you that I'm going to address it later in the slides. That's the worst case scenario. We have a lot of material to cover. It turns out that an introduction to Kubernetes is still a lot of ground to cover. So I'm going to jump right in. All right. So first of all, what is Kubernetes? Well, the easiest way to sum it up is that Kubernetes is a container orchestration framework. It's very well suited for applications that scale horizontally, stateless applications. However, it can also accommodate portions of your infrastructure that do not scale horizontally or stateful applications. Don't let anyone else tell you otherwise. This is a big sticking point in the community, as a lot of people think that it can't do this and they don't use it for that reason. It certainly can, and we're going to show an example of that. So how do you use it? Well, presumably you've written an application. So step one is to package your application components as containers. Then you run the containers on Kubernetes pods, and then you let Kubernetes manage the pods for you. So why would you go through all the hassle? And I'm not going to lie, it can be a hassle. That's one of the hardest things about learning Kubernetes is it is a lot of overhead. Requires a lot of study, I guess. Well, Kubernetes can manage resources for you. It can change the number of running pods to meet the traffic needs of your application. So you can tell it, I want during certain events to scale up to this number of pods, and it will do that for you. You don't have to manage that. It can adjust the compute resources to meet compute demands. And as we'll see in a few slides, Kubernetes runs on a cluster of virtual machines or actual machines. Kubernetes can manage how many virtual machines are in your cluster, and this translates directly to the costs of using a cluster in, say, Azure or AWS. It can also manage resources by replacing unresponsive pods with new ones. So if your pod fails for any reason, Kubernetes is monitoring it, and it literally just throws it away and creates a new one for you. So that was a lot of words. Let's look at it in some pictures. I'm going to show you what a high-level development walkthrough looks like. So as we mentioned, first of all, you start with your application. You've built this. It is packaged as a WAR file or a jar file if you're a Java person, which I happen to be, or whatever packaging format your preferred language uses. But for our purposes, you can think of this as a jar file. Then you package that jar file into a container. The container solution I use is Docker. I can never remember the name of the other one that is growing in popularity, but for our purposes, we'll just think of this as a Docker container. Then you publish that container to an image repository that your Kubernetes cluster is able to see. Then, once you have a Kubernetes cluster, you deploy a bunch of pods to it. And we're going to talk in a minute about what pods are. And then each of those pods pulls your application and starts running it. And then Kubernetes takes it from there. It manages the pods, it creates new ones, et cetera, like we mentioned on the previous slides. So that's simple, right? I said it was complicated. Okay, so now we're going to get into the weeds a little bit. As I mentioned previously, Kubernetes runs on Kubernetes nodes. These are the possibly, I would say even probably, virtual machines. I don't know, people tend to run Kubernetes in the cloud, which means you're running it on virtual machines. And as I kind of hinted at earlier, the fact that they are virtual machines, if that's how you choose to deploy it, gives you more options on how Kubernetes can manage starting and stopping compute resources. But the nodes, are the actual machines or virtual machines that make up your Kubernetes cluster. They are the compute resources. Kubernetes' job is to schedule pods to run on these nodes. Kubernetes can, as we mentioned before, can change the number of nodes to increase or decrease compute resources. Okay, so now another note. Anytime we see a slide that's prefixed with tool, there's a couple tools I use for the presentation. This is the first one we'll talk about, Minikube. Just want to briefly mention these, and I provide a link at the bottom of the slides so that you can research these on your own. We don't have enough time to talk about them all, so I'll just give you a brief overview of what they do, and I introduce them as we have learned enough to talk about what they do. So the first tool is Minikube. Minikube is the easiest way to install, this is important, a single node Kubernetes cluster on your machine. It is for development purposes only. It is a waste of resources to run a Kubernetes app on a single machine. The whole point is running it on multiple nodes. So Minikube is for development purposes only, but it is actually very good at that. It looks to all of the tools created to manage Kubernetes clusters. It looks just like a real Kubernetes cluster. I mean, because it is a real Kubernetes cluster. Okay, so now we're going to start building up a diagram over the course of the next few slides. And we're going to start with this. So here is our 2-node Kubernetes cluster. I want to point out that I drew in 2 nodes here because I keep talking about multiple nodes. This is already diverging from what I'm actually running on my laptop because I'm using Minikube, and as I mentioned, it only has 1 node. But it's also important to mention that nothing in your application that you write even knows how many nodes are running on the cluster. That's abstracted away from you. You package your application and deploy pods, and you don't really get to decide how many nodes it runs on. That's not entirely true, but it's best to think of it that way, that you don't get to decide that. Your systems administrators get to decide that, essentially. Okay, so I have mentioned pods probably 100 times already, so let's finally talk about what they are. Pods, and this is important, not containers, are the fundamental building blocks of a Kubernetes application. A pod is a group of 1 or more containers, so that's how they're related to containers, that work closely together on a specific task. In the demo I'm doing, by the way, each pod only has 1 container. If we have time, we can talk about scenarios about where you would maybe want to have more than 1 container in a pod. But for our purposes, pods and containers, a pod contains 1 container. What kind of distinguishes pods from containers is that a pod manages the volumes for your containers. When you create Docker containers, for example, you get to tell it which volumes to mount, but you don't actually get to manage those volumes as part of your Docker container. Pods allow you to manage the volumes for the container. Inside of a pod is where we also specify health check endpoints for the containers. So the pod specification is how we tell Kubernetes to watch these pods to make sure that they are still functioning and don't need to be replaced. Finally, the Kubernetes software itself is actually deployed as pods on the cluster. So now we can go to the next picture. Here we have 2 Kubernetes system pods, the DNS pod and the API pod, deployed in our cluster. This is part of what makes a Kubernetes cluster a Kubernetes cluster. Now, there are plenty of other pods that make up a Kubernetes cluster that we're not even going to talk about. I mentioned these 2 to show you, first of all, that Kubernetes actually is a Kubernetes app itself. And second of all, these are 2 pods that we're actually going to be talking about. The DNS pod is the first step in DNS resolution for any pods in your cluster. In other words, when you install a pod to a Kubernetes cluster, it is automatically configured to attempt resolution, name resolution, with this DNS server. And the API, which we'll talk a little bit later, all the tools we're using that talk to Kubernetes do so through its REST API. And some of them, like some of the tools we'll talk about in a minute, are very thin wrappers over that API. And what this really means is you're free to write your own apps that talk to the API. So now we're going to start getting into what I'm actually going to deploy to this cluster. So I wrote 2 sample applications that suggest random subreddits. The first one is stateless. The list of subreddits is 280 subreddits, and it just selects one at random and shows you what it is. The list never changes, and so this pod doesn't need to store anything anywhere. That's what makes it stateless. The second application is stateful. It selects also from a random list of subreddits, and it starts with a list of 280 subreddits. However, each time it selects one and recommends it, it removes the selected subreddit from the list, and then it persists the new list -1 item to disk and then it uses the updated list to service the next request. So that's a stateful app. And you can think of the difference between these two as the second one is you're guaranteed to see every subreddit before they recycle. Because what I didn't mention here is that the app won't break when the list runs out. It'll just use the one in memory and start the whole countdown again. That's not that important, but that's how you can think about the difference between these two applications. And we'll show those in the demo. Okay, so now an aside on pods. This will get into some details about how we architect our applications. Pods come and go. They're replaced if unresponsive, and they can actually be deleted on one node and added to another node. This is how Kubernetes moves pods around. For example, if you decide to scale up compute resources from 2 Kubernetes nodes, again, these are the virtual machines, to 5 Kubernetes nodes, it's going to redistribute your pods accordingly across those nodes. And there's no such thing as moving one process from one machine to another. So what happens is it deletes the pod and then recreates it. This is in bold. It's really important that you understand this. You don't get to control either of these things from happening. Kubernetes just does this. This is part of how it manages pods. So when these two types of things happen, when Kubernetes kills a pod, or in particular when it moves it, by default, the volumes that it had on the first node don't follow it to the second node. By default, the new pod that starts up doesn't have the same host name as the previous pod. This is not a big deal for our stateless application or any stateless application. However, this definitely needs to be addressed for the stateless application I just talked about, because as we mentioned, it is saving something to disk. So if it gets moved to another node, it needs to be able to mount that same disk. All right, so time to talk about another tool, Docker. Just mentioned Docker. I think a lot of people have probably heard of it. I use Docker in this presentation because as I mentioned earlier, our packages are packaged as Docker containers. I'm sorry, our applications are packaged as Docker containers. And we need to publish these containers to Minikubes Docker server. So I'm using it to package our apps, and then I'm using it to push those images to the image repository that we had in the application overview in the very first 5 or so slides. Okay, so now we're going to deploy our applications to the Kubernetes cluster. So here we have our stateless app, and here we have our stateful app. I'm going to talk about in a second, the pound signs in the stateless app are referring to the fact that Kubernetes is going to randomize those because all of the pods need a distinct name. We don't really get to choose what that name is because, as we mentioned earlier, we kind of don't care. However, the stateful app has very predictably named pods, and we're going to talk about that in a minute. Okay, so I've been talking a lot about pods, so it's very important to point out that no one creates pods directly. Instead, you create a controller that manages the pods for you. So when I said that Kubernetes can do things like scale pods up and down, it cannot do that if you're manually creating pods. Instead, you use a controller, which is a higher level abstraction, and allows you to say things like, Kubernetes, these are how many pods I want in this application. So the first controller we'll talk about is Replica Sets. And like I just mentioned, a replica set allows you to state how many pods you want. Each of those pods is treated as if it were stateless. In other words, their volumes don't follow them, and they don't have predictable host names. From the application's point of view, pods in a replica set are indistinguishable from one another. And we're going to talk about a little bit later about how we route outside traffic. When I say indistinguishable, when outside traffic comes in and it needs a request to be serviced, any pod in a stateless application is equally adequate for servicing that request, if that makes sense. We'll go into a little more detail in a couple minutes. So the next controller we're going to talk about are deployments. A deployment is just a replica set with more features. I'm not going to use any of those extra features. However, I am going to use deployments because of a tool we're going to talk about pretty soon called Helm that I use to create Kubernetes deployments. Helm will produce a skeleton deployment for you, and by default, it uses deployments in that skeleton deployment. And There are reasons to use deployments over replica sets. Like I said, I'm not going to go into any of those reasons, but it is the best practice to use deployments instead of replica sets. And finally, stateful sets are the last controller we're going to talk about. Stateful sets manage pods that are required to have state. Namely, pods in a stateful set each have a persistent network identity. That gets back to the slide where I pointed out that they each have a predictable name. That's what I mean by network identity. Pods in a stateful set each have persistent storage. And I think I say this next, yeah. Persistent in both of these statements means that they follow the pods across events like restart. And this is, of course, very good news for our stateful application. This is how we're going to deploy our stateful application. Okay, another tool, Kube Control. So Kube Control is a tool we can use to update components in our cluster. And when I say components in the cluster, I mean basically any of the blocks I drew on that diagram, pods, stateful sets, any controller for that matter, deployments, and some more components we're going to talk about here in a little bit. Kubernetes can update any of those. It really shines in inspecting components in your cluster. Kubernetes or Kube Control is the go-to troubleshooting tool for Kubernetes. It can also create any of those components. And if we have enough time in the demo, I'm actually going to use it to do that. But for the most part, we're going to use another tool that I already mentioned to create components, and that is Helm. Now, Helm is a tool for packaging and deploying Kubernetes applications. Just like Maven is a tool for packaging Java applications into wars and jars. So just like you would never, so when I said that we don't use Kube Control to create our components, just like you would never deploy a Java application by copying class files from your local machine onto the server's lib directory, you would never deploy a Kubernetes application by using Kube Control to create your components one by one. You would create a Helm project, which is at a high level just a collection of YAML files that specify the components, and then you would package them, and then Helm provides the tools to deploy that to the cluster. Okay, so here we're going to show our controllers. So here we have a deployment, here we have a stateful set. These are the controllers we're using to manage the respective apps. We're using the deployment to manage our stateless app and the stateful set to manage our stateful app. Okay, so now a little more detail on stateful sets so that we can finally finish off our picture here. Stateful set pods have persistent volume claims. Now that's just a word, persistent volume claim, that's another Kubernetes object. We're not going to go into too much detail about what it is other than to say persistent volume claims are used to request persistent volumes. And persistent volumes are volumes that survive pods being moved or replaced. So you could think of a persistent volume claim as a set of coordinates that points into some external file share, like S3 on Amazon or Azure Blobs on Azure. It is just a claim into an external share where space has been allocated for this pod. And when the pod is deleted and then recreated, it's given the same set of coordinates in the persistent volume claim so that it can mount the same disk that it had before it was moved. So here's that in our picture. Here we see each of our stateful app pods now has a persistent volume claim. This is part of the specification. And that persistent volume claim is just a set of coordinates that points into some external file system or data store. One more thing to complete our picture. So I've been saying that stateful set pods also have persistent network identities. The way that's achieved is through a headless service. Headless service is also another Kubernetes object that we're not going to go into very much detail about what it is, other than to say that it's used by the Kubernetes DNS pod, and it's what allows pods to keep their host name by keeping track of their IP address even when it changes. And when I say even when it changes, I mean when a pod is moved from one node to another, it very likely, maybe 99% of the time. I can't imagine a scenario where it would. It doesn't get to keep the same IP address, for example. So it's the headless service's responsibility for tracking that and updating the Kubernetes DNS pod. So we can think of a headless service as just kind of a DNS configuration file. So up here we have, when we create the headless service, it just maps stateful app pod names to IP addresses, and these are free to change, like I mentioned. Just a note on this name here, stateful app is the name of this stateful set. Default is the namespace that it was created in. Service is just hard-coded saying that this is a service, and cluster local is the default top-level domain for Kubernetes applications. You're free to change that, but remember, I don't know that you would want this to be solutionstreet.com. That's handled elsewhere. This is just the top-level domain for pods within your cluster. So this is what, if this stateless app needed to, if this stateless app pod needed to talk directly to this stateful app pod, the DNS resolution would go here, and it would tell it that that stateful app pod is, stateful app 0's IP address is 192.168.1.100. Just trying to point out, this DNS name is used for intra cluster DNS name resolution only. So it's all a long-winded way of saying who cares what the TLD is here. I don't know why you would want to change it. Okay, sorry, I lied. We weren't finished drawing the picture yet. Now we need to talk about load balancers. So I mentioned a long time ago, how do we manage traffic coming in from the outside trying to get to our pods? We do that with load balancers. Now, load balancers have an internal cluster IP address. They also can have an external IP address, and that's how we manage traffic coming in from the outside. And the key to what they do is they distribute requests sent to either IP address to all pods targeted by their selector. I don't know what algorithm they use. I don't know if it's random, round robin. I suspect it's not round robin, as we'll see in the demo, but you can probably configure that somewhere. But you could just think of a load balancer as an endpoint to the outside world to actually use your service. So here's what that looks like. This load balancer, stateless app load balancer, is configured to distribute traffic among exactly the same pods that the stateless app deployment is responsible for managing, and analogously for the stateful app load balancer and the stateful app stateful set. Okay, finally, it's time for the demo. So let's talk about what we're going to do. And full disclosure, I've already done this in the essence of time, so I'm probably, this slide is written in the present tense, but most of this is past tense because this is already up and running. So I've already started our Kubernetes environment, Minikube. I've configured the Docker CLI to talk, CLI is command line interface. I don't know if that's a common abbreviation. I've configured the Docker CLI to talk to Minikube's Docker host. I've built our 2 sample applications, packaged them as Docker containers, and pushed them to the image repository. And that ability to push them to the image repository is what required the previous bullet. That's what I mean when I say I configured Docker to talk to Minikube's Docker host. I've then run Helm and deployed our Kubernetes components. I've proxied local ports to connect to our load balancing services. So that's just a step I needed to take because I'm not going to give them public IP addresses. So I've just proxied local ports. And that's something that Minikube does for you if you know the proper command line syntax. So a final note before I show you the demo. As I mentioned, Kubernetes, I'm sorry, Minikube only has 1 node. So I had to adjust our picture to 1 node. And for technical reasons, for something that's going to be easier to show in the demo, I've only deployed 1 stateful app pod. So this is the picture. I'm going to leave this here in case anyone has questions so we can refer to it. But this is actually the picture of what our demo looks like. One of the reasons I went through all of these pictures is so that when I show you what it actually looks like, so Kubernetes ships the tool called the Kubernetes Dashboard that allows you to look at the cluster. I think the picture is a lot better to look at than this, but we see all the same components that we've talked about. We see that we have deployments, pods. Now, when I said that Replica Set, that the deployment was just a replica set with more features, Well, the way it gets those extra features is that it creates a replica set for you and then adds features on top of it. So that's why we see a replica set here. And then we also see that we have a stateful set. So down here we see, here's our one deployment. Here's our 4 pods. These ones with the weird names are part of the stateless app, as they say. The stateful app, again, has a very predictable name. Then we see the replica set that the deployment created for us. We see our stateful set. We see the services I mentioned. Kubernetes is an internal one that we don't need to worry about. Here is the headless service that gives the pods in our stateful set predictable names. And here are the 2 load balancers. I don't know why they don't show up as green. They're working for us, so we don't need to worry about it. But anytime I've run this application, they don't show up as green. And I suspect that that is because maybe they actually do expect an external IP address, which I haven't given them. So not an issue. They still work. It is slightly disappointing that they don't show up with a green check mark next to them. We actually see that it lists our persistent volume claims for us. So this is the persistent volume claim that stateful app 0 pod is using. And we don't need to worry about secrets. I didn't create those, so we're not going to talk about those. So let's take a look at the apps. So here is the stateless version of the app. Read the disclaimer at the top. I'm not going to click on any of these random subreddits because I think that's dangerous for a presentation that's being recorded. But when we refresh it, what I want you to look at is I want you to watch what I'm highlighting right here. I want you to watch the host name as I refresh this a few times. I think you can see that it's changing, especially if you just look at the characters after the last hyphen. That is actually our load balancer working. Now, the reason I suspect it's not round robin, as I said, is we see a few of them appear multiple times in a row. So I don't know how it's doing it, if it's random or if it's round robin, but we're able to prove now that our load balancer is working. Now, what I'm listing here is the name, host name, audience, and description for the subreddit. I only point that out because for our stateful app, I actually list one more field, and that is the remaining subreddits. So what we can do on the stateful app, first of all, when I refresh this, you'll see that the name doesn't change. That's not because it's a stateful app. That's because we only have one pod in the cluster. So the load balancer is sending all traffic to that one pod. And this gets into the reason why I only deployed it with one pod, is if there were multiple pods in the stateful app, it would distribute traffic between them, and it would be more confusing looking at this remaining number countdown, because we would essentially be counting down 3 tallies instead of 1. So that's why every time I refresh this, it decreases by 1 in a predictable way. So what I'm going to do is I'm going to bring it down to, say, 240. I don't know if you noticed, I missed 240, but 239. I don't know if you noticed what it started at. It started at 280, which is what I mentioned in the very, very beginning, how many subreddits there actually were in the list that I'm using. So now what we're going to do, make sure I get the right one here. These are just some scripts that I wrote to automate this part of the demo. So I'm going to kill a stateful pod. Actually, not just a stateful pod, the stateful pod, and I'm going to bring this window up so that hopefully we can catch it in time and watch Kubernetes bring the cluster back to health. All right, there it goes. So there's one stateful pod. Yellow, I think, means that it is not responding unless we missed it going red. I'm not sure. You'll see yellow and red, but this is Kubernetes telling us that, you know, our pods are sick right now. Oh, there it goes red. So this tells us that the pod, Kubernetes has decided that this pod is dead. So it was polling it for a little bit, and then it decided it was dead, and now it started a new one for us. Now, I just want to point out, all I did was kill it. I didn't do anything else. Kubernetes brought it back to health for us. But now the big thing that I want to prove is, I want to prove to you that this app is backed by a pod that we witnessed get killed, we witnessed it disappear, and we witnessed it come back. So the big question is, when I refresh this, how many remaining subreddits are there going to be? Now, if it was a stateless app, I would assert that this number would go back up to 280, and I'll prove that to you later. But because of the magic of stateful apps, when I refresh this, it just starts counting back down at 39 again. Now we're down to 230. So I know that because everyone's on mute, I can't hear the oohs and ahs, but I suspect they're there. Now what I want to do is, remember earlier when I said that I would use kube control to deploy an app instead of Helm, I'm going to use kube control to create a deployment, and it is going to, yes, I'm sorry. Just want to make sure I was doing the right thing. So I'm going to deploy a deployment now that instead of using the stateless app pods like our previous deployment, it's actually going to use the stateful app pods. And this is an example of something you shouldn't do. In other words, I am taking an application that I have declared to be stateful, and I am deploying it as a stateless app. And that's why I call this the stateless stateful app. And now we can watch. So now we see we've added a deployment, and Kubernetes is bringing it up. We can see that we've got an extra replica set now too, where we've only had one because the deployment created that for us. Nothing has happened to our stateful set because we haven't touched it. All right, now we're all in business. So now, if I come over here and load this app, again, this is the stateful stateless app. It looks just like the stateful app, right? We have the same field here. And when I refresh it, it still counts down. However, let me bring this back up. When I come over here and do what I'm calling kill the confused pod, because the confused pod is the one that is stateful but deployed via a stateless controller. I've seen this before. I'm not sure why two pods go down when that happens, but never fear, Kubernetes is going to manage it all for us. While we're waiting for it to come back up. All right, let's back up. So I do want to prove a couple things. This is the original stateless app, still running, no harm done. This is the original stateful app, still running, no harm done. So these are all running at the same time. Now when I come back here, now we burned through a couple subreddits and we got the number from 280 down to 254, and then we moved this pod, but in the context of a deployment, not in the context of a stateful set. So now when I refresh it, it goes back up to 280. That means that you know, we've misdeployed this application, if that makes sense. Okay, I'm looking at my clock. I've got half an hour, so let's take a look at some code. I'm not going to take up the whole half hour. We're going to leave plenty of time for questions. But there is one piece of code that I want to show you. We've been talking a lot about Kubernetes objects, right? And it was a lot of magic. I just said we use Helm to deploy them. Well, this all fits on one page. So this is what our deployment looks like. Again, our deployment for Helm is just a collection of YAML files, and each of those YAML files can specify one or more Kubernetes deployment. I'm sorry, I said deployments, one or more Kubernetes components. So here we have an example of, this is exactly the deployment that I used. So for any Kubernetes object, you have to specify what version of the API that object stems from. Then you have to tell Kubernetes what kind of object it is. This is a deployment. And then each object has some metadata. I believe they all have the name metadata. So this is the name of the deployment that we've been seeing in the application. And then each Kubernetes component has a component-specific spec, if that makes sense. So for a deployment, that spec contains a number of replicas that we want to deploy. As we've said multiple times, we're deploying 3 replicas. And then I briefly touched on the idea of a selector when I was talking about load balancers. The selector is what tells a Kubernetes component that is responsible for managing or corralling, or, you know, so I would assert that deployments manage pods. Services corral them, for lack of a better word. Services don't, but anyway, there are multiple components that act on a set of Kubernetes pods. And this is how we tell them what pods that they act on. So here we're saying this deployment acts on any pod that has a name stateless app. Now the template, it's important to notice the distinction here. When I said that no one deploys pods directly to a cluster, that is true, but you're free to do so, because just like we have a deployment object, there's also a pod object. But the deployment creates pods for us. So if you were to create a pod, it would look exactly like this. In other words, and then you would just put pod as the kind. The template is a pods template when we're talking about a deployment. So for each pod, we're saying that its name is stateless app. It is kind of annoying that you have to specify that twice, but they mean two different things. This is the name of the pod. I'm sorry. This is not the actual name of the pod. This is the name label for the pod. So multiple pods can have the same name label. However, they cannot have the same name, if that makes sense. We could have picked whatever we wanted for this label. I called it name. You can call it app. It doesn't matter. But yes, these two have to match. And I think tools like Kube Control might actually be smart enough to enforce that they match for you. Then in the pod spec, we also have to tell it about our containers. So the container, the name you get to pick, this is the name of the Docker image that I packaged my app in and then pushed to the image repository. Image pool policy is not important. Here we tell Kubernetes what ports our pod exposes. So, and we get to give them a name, and the name is useful because when you refer to them later in services, you can refer to them by name and not by port number. So here we say the container port is 8080. If you don't specify the, I'm going to say host port, but I'm not sure if that's what it's called. It assumes it's the same. So this is telling Kubernetes that this pod exposes port 8080, and that port 8080 will go directly to this container inside of that pod. The protocol TCP, you can also specify UDP if you want. We don't care about UDP because HTTP is a TCP protocol. And then I mentioned earlier that we need to tell Kubernetes how to monitor our pod. And the way we do that is through a liveness probe, which is used periodically when Kubernetes is, I think, like every 5 seconds by default, is checking to see if your pod is still alive. And then there's the readiness probe, which Kubernetes uses when it brings a new pod up. It keeps, for us, they're both the same, but you can imagine scenarios where you would want them to be different. So Kubernetes gives you the granularity to make those two separate probes. And again, all I'm doing for that probe is Kubernetes is making the same request that I'm making in my web browser. And then all it does, Kubernetes, now let me go into a little bit more detail here. When you tell Kubernetes that it's an HTTP GET probe, Kubernetes is smart enough to realize that, oh, that means I hit whatever URL they tell me to on whatever port. Here, we're already using this name for the port instead of the port number. And if I get an HTTP 200 response back, I'm going to consider that success. So for other probes, I think they have more detailed ways of telling Kubernetes how to determine success or not. But because we're using one of the out-of-the-box HTTP GET probes, Kubernetes already knows what success is. All right, I'm not going to read through this whole slide, but these are just some tools I use to produce this slide. I believe we're going to produce the PDF for download. All these links are clickable. I wrote the apps in Kotlin. I use Spring Boot. I use Gradle to build them. I use Dia to draw all the diagrams. And I used a tool called LaTeX with a package called Beamer to produce the presentation. If anyone's interested in that, certainly I encourage you to look it up. This is interesting, where I got my subreddit data. There's a website that provides bulk data on subreddits. So I just downloaded one of the files. I think it was gigabytes in size. And then I did some filtering to try to make sure that I found safe subreddits in case someone asked me to click on one during the demo. And then finally, this whole demo itself is all on GitHub, so you can download it, play around with it yourself. Certainly reach out to me if you have questions. The instructions for building it are probably could be fleshed out a little bit. So I'm not going to read this whole slide. A note on capitalization. I agonize over what to capitalize and what not to. These are the choices I made on how I capitalize things. I will point out that I cannot bring myself to capitalize things that I type at the command prompt, which is why Docker, Helm, Kube Control, and Minikube all started with lowercase. And that's it. Does anyone have any questions? Does anyone want to go back and look at different code? I have the actual code that I wrote the applications in. I have the YAML files if anyone wants to look at those.
Hey, Ed, this is Joel. Can you just talk a little bit about if or how things are different when running, on AWS or Google Cloud? They seem like they all have some sort of Kubernetes type services. What's different, or is it pretty much exactly the same?
The first thing that is different is how you provision the cluster, for example. So I can speak to Azure. Azure has, it's called Azure Kubernetes, and then it has an S, and I don't know what the S stands for, but AKS is how it's abbreviated. So each cloud is going to have a cloud-dependent way of actually provisioning a cluster. And that cloud-dependent way will let you say, like, these are how many nodes I want to run on, or some of the fancy ones like Kubernetes will let you say, this is I said Kubernetes, like Azure. I know for sure for Azure because I've done it on Azure. I'm not saying that AWS doesn't have these features or GCI. I'm sure that they do. But I know that on Azure, when you provision a cluster, you can say, I want 3 nodes, for example. Or you can say, I want a minimum of 3 nodes, and I want a maximum of 10 nodes. And Kubernetes, you figure out how to distribute load. And that's one of the primary ways to control costs. So, and that's kind of where I draw the line. Provisioning the cluster is platform dependent. However, once you have the cluster provisioned, deploying apps to the cluster via a tool like Helm, for example, is platform independent. And provisioning the cluster is usually a pretty small part, if that makes sense. Does that answer the question?
Got it. Yeah, thanks so much.
Anybody else? Any other questions? Going once? Going twice? Okay, I'm going to stop recording.